Thanks all for coming. Today at the Science Hour, I'm going to talk a little bit about the atmosphere-only runs we've done and a little bit of analysis I've been working on, in the last few months. Something about improving our EERIE composite algorithm. So most of you are probably aware of the atmosphere-only simulations that we've been doing as part of EERIE at ETH and also at the Met Office. But just as a recap, and maybe for any new participants, I'm just going to run through it for a few minutes. So as you all know, EERIE is focused on doing high-resolution coupled ocean atmosphere simulations to look at the role of eddies in weather and climate. And in comparison, we're also doing these atmosphere-only simulations. This is done for two reasons. First, we get a comparison baseline to the coupled simulations over the historical period, where we just constrain the SST to the historical evolution. And so we don't suffer from any model drift, any SST biases, and so forth. Secondly, we would like to really study the impact of having ocean eddies on weather and climate. Just with high resolution coupled simulation, this has the difficulty is that there's a lack of a baseline, so we don't really know how the situation would have been in a model world without eddies. And of course, there are experiments one can do with a coupled setup to study this, for example, by lowering the ocean resolution such that the ocean is not eddying anymore. But this also changes a lot about the ocean. It changes the ocean mean state, it changes the ocean atmospherability, and it just changes a lot of things that are hard to control for. So the idea was, with atmosphere-only experiments, we could have a test bed to study this in more detail, because this setup gives us complete control over the SST boundary condition. So we can manipulate this very ad hoc, very consciously, and look at the impact that this has on the atmosphere. Of course, this has downsides. We deteriorate the air-sea interactions. They will be less realistic because we assume infinite heat capacity ocean, so to say. But we still think this is a useful comparison to the coupled simulations. Just to look over the simulations that we have done. There are, again, as I said, two sets of experiments conceptually. They're the reference experiments. So these are simulations forced with historical observed SST. We looked at this quite a lot, and I'll show another plot in a few slides. And we chose in the end the SST taken from ESA CCI version 3, which is really quite a good product going back to 1980. The AIM simulations are done by IFS at ETH and by the Met Office model at a few different resolutions. Basically, a high resolution setup that mirrors the coupled simulations, and also a lower resolution setup, with whether the resolutions differ slightly between the IFS and the Met Office. There's a slide, and at low resolution, we also have a 10-member ensemble. We have a slight typo here. We now have 10 members at 28 kilometers. So this gives us a lot of data to compare to the coupled models and to study these impacts. And secondly, there are the idealized simulations where we smooth the eddies. So how we do this is we take the high resolution SST from the observations, we compute a daily climatology, which I can talk about more if somebody's interested, and then we compute the time varying anomalies from that. And to these time varying anomalies, we apply a spatial smoother that is inspired by the Rossby radius of deformation. So we will want to smooth those eddies according to a physically based length scale. And how this then looks is one snapshot you can see in the bottom right. So on top we have one snapshot of the observed SST, which is distributed at 20th of a degree, and at the bottom you see the same time where the time varying anomalies have been smoothed, but notably the climatology has not been smoothed. So you can still see, if you can see my mouse, the sharp gradient in this Gulf Stream region that here comes from climatology, whereas all the small scale variations have been smoothed over. The setup also gives us then the ability to do the reverse experiment where we smooth only the climatology, but not the anomalies. This is a bit lower priority, so we've only done this as low resolution so far, and this has not been the priority to investigate, but this gives us the comparison experiment. of the impact of the fronts rather than of the eddies. I should have said in the beginning, if anybody has any questions, please just interrupt me in case something is not clear. And just to sort of summarize how these sets of simulations look, well, how these set of experiments and what that means for the SST boundary condition, I've just tried to summarize it in this figure, which basically follows from the last slide. So on the top, this basically one snapshot of SST in the top from the observations with smoothed anomalies and with smooth climatology. And the second row shows the difference to the observations, to the unfiltered field, where the difference is quite clear in the eddies and in the fronts. What this then means for the boundary condition is that there's a strong difference in SST variability. So when we look at the variability standard deviation of the SST anomalies, you see the strong anomaly standard deviation in the observed in the unfiltered field and also with smooth fronts, because we maintain the eddy structures there, but it's strongly reduced when we've smoothed over the eddies. In comparison, the whole construction of smoothing the eddies, but not the whole field, the whole SST field, was that we did not want to see a mean change in SST. And this is exactly what we see in the bottom two panels, where I just show the mean SST over a month, I believe, where the two left panels are essentially identical as shown by the difference on the bottom. Whereas if we smooth the fronts down here, you see that this does induce a mean SST difference. And this is exactly what we wanted to isolate. We really want to look at only the difference in the local eddies and not in mean SST or any other things. Yeah, just another reminder, this is how this is the kind of plot that inspired us to pick this SST forcing data set. So we looked at a number of data sets, notably Ostia has often been used, also from the ocean reanalysis GLORIS, which only starts in 93. But you see that many of these Ostia ESA inspired data sets in the early period have these large fluctuations in, say, daily global mean SST. And this is what we wanted to avoid. And ESA CCI version 3 really strongly improves over this. In future analysis on the coming slides, I also look at a few observational products to compare our simulations against. One is precipitation from GPM iMatch, which is often used for this kind of small scale local precipitation. It's quite reliable in that front. And we're also looking at surface winds, which is a product distributed through Copernicus, which essentially bias corrects R5 winds based on a couple of observational products. Just to start off, an overview about the simulation. Some of you will have seen this already, but as a reminder, the global mean metrics that we see how the simulations compare to observations and to each other. So here we're showing the global mean, monthly mean of surface air temperature, top of atmosphere radiation, precipitation, excluding the high latitudes, and total cloud cover. In blue and green are our two simulations, so the IFS simulations at low resolution of 28 kilometers in green and at 9 kilometers in blue. And because we have a 10-member ensemble, you see a shading in the green. The other two simulations here, N216 and N640, are the simulations from the Met Office that I have, so we can compare those as well. And then we have observation-inspired products, R5 series for top of atmosphere radiation, and two precipitation products, GP and iMatch, as I mentioned, and another often used product called GPCP. So the 2-meter temperature follows R5 quite closely, and of course, this is sort of an easy bar to pass since the SST are constrained to observations, and we don't expect we cannot really get any large deviations from there. Still, it's good to see this agreement, and there are already some interesting things in here that we might look at more in the future. For example, it seems that the Met Office simulation here, the yellow line, has a close agreement to R5 in the last 10 years or so, and speculation. One speculation might be that this could be due to the aerosol forcing, which is one thing that the only real forcing difference between our and the Met Office simulations. So there's still a lot of things to look into that we haven't looked at. In terms of top of atmosphere radiation, series is often sort of the gold standard to compare to. So this is the gray line, and the IFS has been tuned in the configuration we use to reproduce this. So as expected, we get quite a close agreement between the blue and the gray line, so between our high resolution simulation and series. And we made the choice to use the same tune settings also for the lower resolution configuration, but you can see by the green that this doesn't match as well, simply because this is essentially resolution dependent and we've chosen to use the same parameters. This does not have any large impacts in our simulations because we use an atmosphere only configuration. But this might be something to consider to look into in coupled simulations, where this could induce ocean biases and such. Precipitation follows AR5 relatively closely, but the interesting thing here is the divergence between the observational products, where GPCP is quite constant in time, but with an offset, and GPM image has a very peculiar temporal trend, which I think we should not trust very much. But this just shows the large deviation the large uncertainties that are there in observational precipitation products. Yes, but what I really want to talk about is looking at the local impact or the local eddy features that we see in the atmospheric impact from these simulations. So many people in EERIE doing eddy tracking and eddy composites. And so we also want to do this in the atmosphere-only simulations. It seems the agreement has been to use this package called PyEddy Tracker. And thanks to Malcolm, we already have the eddy tracks based on observed Aviso sea surface heights. So we can essentially use those also in our AMAP simulations where we don't really have to track the eddies because the ocean is not there. And the assumption is that the eddies identified from the observed Aviso product from sea surface height match the eddy signatures that are there in the ESA CCI SSD. So essentially, we're also looking at the agreement between these two separate observational products. But we do not separately have to track the eddies like in the coupled simulations. So we already looked at this quite a long time ago, probably I think starting in the first hackathon where Dian and Aaron and many other people are very interested in this. So we came up with a sort of naive eddy composites. I guess we could call those, but we could come up relatively quickly. And what we basically did is we just drew a 2x2 degree box around each eddy that was identified, and we averaged all of those. Often first with a high-pass filter applied, for which we used the same filter that we also used to filter the SSD. So we used to generate the boundary conditions. So we used this filter with a spatially varying filter length scale that was inspired by the Rossby radius of deformation. And this was quite useful and it was a very interesting exercise. And we already got plots of this kind long ago, which showing the eddy composites at high resolution, or at various resolutions here for Southern Ocean eddies in 2021. And GPN image in the top left, and then the high resolution and low resolution reference simulations, and then the 3 idealized simulations. So one could already see that this was anticyclonic eddies, I think, that we got a signature of the eddies that was on the magnitude comparable to observations, and that the idealized smoothed eddies simulations were successful in essentially removing most of the signal. Still, there were some limitations in this method, notably when we looked at previous studies that looked at the impact of eddies on the atmosphere, on eddy ocean atmosphere interactions. What people often did is they scaled and or rotated the eddies. For example, this study by Frenger 2013, which has inspired us quite a lot, and they had this beautiful composites here of eddies in the actual field, so not in the high-pass filtered anomalies, where they were all scaled and rotated in sort of eddy radius space and with the wind coming from the left. And this gives a quite clear indication in the sort of physical space what a typical eddy could look like. So Chris has been doing quite some work early this year, and we've been adapting this and running it over our atmosphere simulations to come up with a algorithm that can do something similar for our simulations. So what we do now basically is we do composites on the physical field in ±3 eddy radii. So just illustrating, and they're rotated to align with a large scale wind, just to illustrate how this looks for an example of an eddy in the Galveston region that you can kind of see already in the left, sort of, if you can see my mouse, in the center of the screen. And so this is SSD for one snapshot, and superimposed we have the large scale wind that comes here from the North American continent and then turns over the Gulf Stream. And the way how this method works is to, as shown in the middle, to generate a domain that is aligned with the large-scale winds, and then resamples the data into a eddy-centered grid. And this is a really neat algorithm and gives us a lot of flexibility. For example, it is relatively agnostic to the grid. I mean, at the moment, we only use latitude-longitude grids, but which latitude-longitude grid is not really essential here. So it makes it quite easy to compare our simulations, where we typically look at quarter-degree output, and to directly compare these to the high-resolution observations without having to first regrid the data set. And then there are a few parameters to tune or to select. And what we've typically been, centered on doing is to choose 3 eddy radii in sort of X and Y, where the wind always comes from the left to the right, and to choose a point density of 30 per radius. So we have essentially 90 by 90 points in this domain. This is also quite nice. So we can work quite well also with this quarter-degree output, as you will see in a moment. Yes, 1 second, here we go. So just as a summary, we have the eddy tracks from our VISO. So what I'll show in the next slide. So we have the eddy tracks from our VISO. We focus on the Southern Ocean between 25 and 60 degrees south for a period of 2010 to 2021. And this is a lot of eddies, but it's still not all the eddies. There are a lot of eddies in this period and in this region. And it is computation intensive to do this for multiple data sets. For now, we've avoided any eddies that have any regions that have any ice in it, because we know from our colleagues that this complicates the analysis quite a bit. So we've started to just ignore that. And we match the tracked the composite eddies between the various data sets we have, so between observations and the various simulation data sets. So where we can know when we look at a set of eddies that those are the same eddies in all the data sets. Then we can also subselect those by eddy amplitude or SST difference, and I'll show you how this looks in a moment. And we compare these to observations from GPM and from the bias-corrected winds. First, what do these eddies? Where are those eddies, and what properties do they have? So these are anticyclonic eddies, and it looks very similar for the cyclonic eddies. On the top, and here I'm sort of showing a histogram essentially of the number of eddies. So the color bar is the number of eddies in each 2 by 2 degree box. So on the top, we have all 390,000 eddies and how they're distributed over the Southern Ocean. And then the following panels show subselections of these eddies, essentially looking on the strongest eddies. And I'll show you why this is important, or why this is relevant, why we did this in a moment. The top 3 panels here, now the 2, 3, and 4 panels, show where we have sub-selected the eddies based on the SST difference from within the eddy to outside of the eddy. So we just look at within 1 eddy radius minus outside of 1 eddy radius, so between 1 and 3 eddy radii, and just do the absolute difference of that. And with the rationale of this was that we really want to focus on the strongest eddies, and the strongest eddies in the sense of the impact of the atmosphere could very likely be those with the strongest SST difference. Like the atmosphere would see the most of this. This might be slightly different in a coupled model where we also have to think about currents and wind interactions, but in the AMIP world, the main thing, how these eddies are going to influence the atmosphere is through the local SST gradients. But we can also look at the eddy amplitude that PyEddy Tracker conveniently provides, and put thresholds on those. And these thresholds, either of those thresholds are quite intense. Like we really look at only the few strongest % of the eddies. Yeah. So let me just show you how this looks. So these are overall the cyclonic on the left, on the right, and anticyclonic on the left eddies. And let me just walk you through this plot because there are a lot of panels. So from left to right, we have the different variables that we look at. So that's SST, 10-meter wind speed, turbulent heat flux, and precipitation. And all of these fields are daily means. So they're composites of daily means and then averaged over all these 390,000 eddies. And from top to bottom, we have observations in the top, and then the low resolution and high resolution simulations. I'll show later a plot that includes also the filtered eddies. But for now, where we sort of removed the impact of the eddies, but for now we want to look at the representation of these eddies and their impacts in the simulations that actually do have eddies. Yeah, so what we see is first in the SST that, as expected, they all look quite similar, and this is of course what we want because they're all meant to have the same exact SST. You could think if there perhaps some difference from the regridding, because of course we take the high resolution SST and then we grid it to the model, the internal model grid, and then we grid again to the quarter-degree grid on which we analyze. But the difference of this are relatively small. Then we look at 10-meter wind, and a signature is visible, but it doesn't really isolate the eddy as such. And I'll discuss this comparing to the previous paper in a few slides. In the heat flux, the signature is quite notable. And in precip, again, we have the situation that we can see the impact in the sense that these contours are sort of curved, but it's relatively small compared to the large gradient that we have across the box. And perhaps this is because of the Southern Ocean, where we have sort of strong meridional gradients. And if we looked at an area with less intense gradients, we would see less of this. Comparing left to right, we sort of see the difference between cyclonic and anticyclonic eddies. And as expected, these are largely composites. They're largely the opposed. So instead of a warm core eddy on the left, we have cold core eddies on the right. And they have, according impacts on heat fluxes and precipitation. But this is now why we would like to subselect on eddies and look at the strongest eddies, where we can perhaps isolate more of these effects and see more of the impact on, say, precipitation or wind speed. So this is now where we focused on eddies, where this SST difference that I've talked about is at least 1.2 Kelvin. And this is on the order of like 3 or less than 2 to 3% of the eddies on these two left and right sides. And the impact of this is quite striking. So we get a much stronger, impact of the eddies, even in this on the mean field here. So it starts to really isolate the eddies also in precipitation and wind speed, and we get quite strong differences in the heat fluxes here of around 100 watt per square meter. One way now we can combine these two, to get the impact of eddies, is to take the difference between these two sides. So we do the difference between cyclonic, anticyclonic, and cyclonic eddies. And this also has the effect of largely smoothing out this residual gradient that we saw. And here showing this difference between anticyclonic and cyclonic eddies for all the eddies on the left and for only the strongest eddies on the right. And this is quite neat because it that essentially removes this background gradient. And these two plots look very similar, with the main difference being when you look at the color bar at the bottom, that these differences get much, much larger on the right. So it's very nice, and it allows us to look at the impact of eddies, so to say, and also compare the observations. So what we see is that the wind response to eddies is probably a bit weaker in our simulations. Here, whereas the precipitation response is a bit hard to say, but it might be a bit stronger compared to observations. And there are also some interesting slight shifts in the in the composite compared to the eddy center. But we often see these slight deviation, especially in the wind speed, where they're slightly shifted. And I would be quite interested in doing these composites also for coupled simulations and see if this is perhaps a feature of the coupling due to wind current interactions or other things of this kind. But what's interesting is when we now compare this our results to previous studies, for example, to Frenger et al. 2013 that I mentioned before. And what's interesting is they seem to get much stronger local maxima without having to do this very intense subselection that we do. So we really need to go to the top few percent of eddies to get these local maxima and precipitation and wind. And they get much clearer signatures in their analysis. So that's interesting. But still, generally our model and observation data is quite consistent, which is also very interesting. And we probably get a slightly stronger precip response and a slightly weaker wind response. Yes, just to mention the impact, now I'm going to talk a little bit more about actually the impact of the eddies, of removing the eddies, because this is essentially what we wanted to look at, or what's the purpose of these experiments. And this is a plot I showed before. It's this anticyclonic minus cyclonic eddies for all the eddies, for all the around 390,000 eddies. And again, as in previous analyses, we show on the bottom the filtered, the simulation with the filtered eddies at high resolution, and we remove almost all of the signature. So this is good to know that we have removed most of the signature in SSD and also in the other fields then. Yeah, so this is the local. So what I've talked about is the local response to eddies in the simulations. And what we're now looking for is, so we have the local response, and I'm going to show a little bit of a large scale response, and that what we're still sort of missing and working on is the link between the local and the large scale. And we have some process-based diagnostics that we want to work on in the near future. But to show a few slides on the large scale response that we see, this is, I'm showing here the 2 meter temperature differences. On the left, on the left and the center, it's the impact of filtering. So it's the unfiltered minus the filtered minus the smooth anomalies simulation. So you could say this is the temperature difference that is induced, or could be induced if it's significant, by the presence of eddies. And on the left, for comparison, is the bias of the high resolution simulation compared to AR5. And you should note that these color scales are all slightly different. So the two left and center are quite similar. But generally speaking, the impact that we get from the eddies in the simulations is quite a lot weaker than the general bias that we see to AR5. And this is a feature that we see quite a lot in a lot of the variables we looked at, that there is a systematic, small but systematic impact of the eddies in the atmosphere-only simulations. This impact is generally relatively small, so perhaps around 0.2 sigma compared to the variability, and it's generally smaller than the bias. And the nice thing is that we do have those two resolutions, and we have a large ensemble, well, a relatively medium-sized ensemble at low resolution. And there are some consistent features between these resolutions, but there are also some areas of inconsistency. And we're working on looking at this more in depth to see what's really significant here. We've also started looking at the circulation response. So this is the change in zonal mean zonal winds. This is just at high resolution. So again, it's the unfiltered data minus the smoothed anomalies for the 4 different seasons for DJF, MAM, JJA, and SON. And again, there's a small but systematic impact, which I think is a phrase we'll use a lot, of shifting the zonal wind slightly north, the tropospheric jet slightly north. So which could suggest a slight impact, a slight strengthening of the jet, a slight additional influence of the eddies on the zonal winds. But again, the caveat that I already said for the 2 meter temperature, this is not necessarily consistent between the simulations. So taking one panel from the previous slide, just at the difference in DJF on the left and comparing it to the corresponding data for the low resolution, shows that those don't necessarily agree. And we'll look into more if this, if say the left is just randomness, or if it could also be a feature of resolution. Some previous studies have suggested that you really need to have high resolution to potentially resolve some of those impacts of eddies on the mean flow. So we do see differences, but there are also some caveats, and we'll look at this more in the future. And of course, we're always happy for suggestions. What you think is good to look at. Just some next steps and what we're going to focus on. So all this work on eddy compositing fits quite well with the work on work page 5, and we want to coordinate more of them. Maybe they can use this, and maybe it'll take some more things on what's going on there. We need to expand our evaluation. That I've just touched on some of these things here in the end, especially to improve our statistical confidence in those results. And then what I've said is what we're really looking for is a way to link these local boundary layer impacts that we can do quite well with eddy composites to the large-scale circulation that I touched in the end. And the question is how to reliably identify these missing links. And there's some works in progress on this. We're working on warm conveyor belts, but perhaps also the work in Reading could fit in quite well here to give us some answers on these questions. So yeah, we're working on the data description for the reference experiments and then also for the idealist experiments, which should be finalized relatively soon. So we're also very excited about that. So we are very happy for EERIE to fund this work. And we're also very happy that you're here and listening. And if you have any questions, please raise your hand. Thank you.
May I ask a question?
Please.
Yeah, I mean, you said your simulation go from 1980 to 2023.
Yes, that's right.
Yeah, I was wondering whether you think of analyzing trends in the atmosphere forced by the SST trends, large-scale trends, as well as focusing on the eddies, or is that?
Yes, I mean, you mean beyond the large-scale difference? I mean, I've showed some plots at the end, but you mean like looking at the difference in the trends between the simulations? Of course, those are still quite constrained, but this is actually something I would like to look at a bit more. Like we have some people here in our group that look at trends in various seasonal forecast systems and how this aligns. I wouldn't necessarily expect a big difference, again, because they're so constrained and we don't have a difference in mean SST. But this is something to look at more, yes.
Yeah, I was wondering about the trend of increase in winds that is seen in the Southern Ocean, and whether that's something that you see in such simulations, or is it, something that is not a forced signal, so it's really completely all over the place with different members.
Oh, you mean just in the sort of reference simulations compared to observations?
Yeah.
Yeah, I have not compared those kind of trends to observations. I've mainly looked at the mean state and then variabilities.
Okay.
But I'll put that down to look into that more. Yeah, it could be quite an interesting data set because, of course, it's not a reanalysis or something, but it is a sort of ensemble that is constrained by observations, at least in the sea surface. So this would be good to know if we can capture these things.
Thank you. Everybody is silent, so I am going to.
I don't have a. I don't have a question, but
okay.
I just reiterate what I put in the chat. I think one of the things we were maybe hoping to get today was some insight or input from some of the members of Package 5. I don't think Nikki is here, but this in particular, this previous work in the paper by Ivy Frenger and others, like we spent quite a lot of time trying to reproduce or do a similar type of analysis to look at these precipitation responses. And we can get a lot of this similar structure, especially on the rainfall composites, but only if we restrict our analysis to the largest magnitude eddies. And this is a bit of a puzzle, and we wondered whether there's something else that's not maybe 100% described in the methodology of this paper that I'd be quite interested to talk to Nikki and others about. But otherwise, I think Matthias has done a good job of checking the workflow piece by piece, found some of the issues and fixed them. But I don't think we've done anything really wrong. I just think there is a genuine difference between the estimates of the magnitude of this local precip response in the Southern Ocean in the two sort of data sets. And it's not clear why that might be. So I'm not expecting answers here, but if anyone has any good ideas or people, I think we should share these slides with Nikki and WP5 afterwards, because I think it'd be nice to try and get to the bottom of this. It could be the data sets that are different. It could be the tracking, but or the time averaging. Not sure.
Yeah, there was something I didn't understand, because at the beginning you say that GMP emerg, so precipitation product, had very strange trends, but then it's the one you are using for the Southern Ocean. Did you compare for your study of the Southern Ocean eddies? Did you compare with GPCP?
I did not. I mean, GPM image seems to, I mean, I've raised this question internally a few times about what are good data sets to look at local precipitation, and this seems to be quite well used there. I think GPCP is also at lower resolution, so I'm not sure it is as useful to look at these small scale differences. But I did think it was interesting to report at least that their trend was so different. Perhaps this is a different, like changes in observing system, different products being used. I'm not sure about that.
Yeah, it was a really nice talk. Sorry, I missed the first few minutes, and I will watch the recording and get in touch with you. It was actually quite interesting and interesting to see that, as you mentioned, the magnitude is low, which is something we also observed for the composites under the CIs. But there was a part where we were thinking, okay, maybe it's after all the filtering, and you're not using the full fields, and sometimes it's not always comparable. But even when I was sharing it with some other people in the same sort of work, it was coming up that the magnitudes were lower. And once I do it with all the models, so at the moment I have some with Icon and FESM, but I will redo it with the different range of years. And once I have that, I think it'll be interesting to see how much that shift is in your sort of atmospheric variables as well as in the oceanic ones, ocean and ice ones. So we do also see that the magnitude is a bit lower.
Compared to the Frenger previous
compared
studies.
to not just Frenger, but also the eddy ice interaction ones as well. Some of those variables, the values are sometimes a bit weaker.
That's interesting. Yeah,
so sorry.
I mean, some things when you say in the coupled ones, of course, this could be also to model differences and such, which is very interesting. I mean, here we see this in observational products as well. So this was what has puzzled us quite a bit. Yeah.
Would it be the tracking?
I'm not sure. Yeah, it could be that there's. I mean, of course, it was a long time ago. They probably used slightly different algorithm to find the eddies. There's also a reference to there is a line in the paper and in the figure description. It says something. Chris, remember something like each eddy was scaled to their magnitude or something, and I could not find exactly what they meant with this. So might get in touch with Nikki and maybe he remembers.
Yeah. I think I can also once I get to a clearer picture of how much the difference in magnitude, then we can talk about that.
Yeah, it would be great to chat about that more. You've looked at the coupled model so much, and I've been stuck in the AMIP world. Yeah.
So we can still look at it, and I will also look at a few atmospheric variables, but still for the eddies in the CI zone, so not the open ocean. But I think I'm also saving them for the open ocean, so it will be easy to check.
Yeah, great. Yeah, I mean, I also have them that do have eddies. I just filter them out before I do an analysis, so I could look at those as well. I just know from talking to you that is quite involved, so I didn't know exactly what you did to process those. So I might still do that though, once I figure out what exactly you did. Yeah.
Yeah, sure.
I don't know how many there are. I did stop at 60 south. Oh, but still.
Hi, nice talk. I was just wondering this with the zonal mean field that you shown. You did some ensemble, right? So 5 or something. So
you mean these plots? Yeah.
Yes. So these figures are from the ensemble member, like mean. You don't see any consistent signal when you
between ensemble members? Sometimes. I mean, this will be a mean over all the sort of the mean involving all the ensemble members. But I've looked a little. Only 5 members. This was we need to update this for the extended ensemble. But I've scrolled to ensemble members a bit, and like sometimes in some places they're consistent, but in some like just looking at the spatial differences, and sometimes they're consistent, but sometimes they're also not. So that's also interesting. Yeah. I think in general we see that the response is quite small, so it's not like we get this huge forcing that will be then extremely visible in the same way in all the members. I mean, some things will be very consistent. Like, for example, when we smooth the climatology, right, then we induce a mean SST bias.
Yeah.
It's like an additional gradient about the Gaussian, and those will be quite clear, right? But the atmospheric response, there is some variability in there. Okay. If anybody else has a question, I would invite them to raise their hands. Otherwise, I think thank you all for listening. And please get in touch if you have any more questions. And yeah, thanks for coming and have a good rest of the day.